This section is dedicated to talking about area and perimeter. Let's start with perimeter. I find that to be the easier of the two. Perimeter is simply put the distance around the outside of an object. And for the most part, finding perimeter is pretty easy. There will be some examples that might be like we have to do a little bit of work, but they're not that exciting. We'll look at some. So, like for instance, let's say you're asked to find the perimeter of the following. Okay, so here, this will be example part A. So let's say you're told that you're working with an isosceles triangle. And here is the information we are given, that this is 32 millimeters and that this is 34 millimeters. Okay, so if I want to find the distance around the outside of the object, technically I need all three sides. But because we're told this is an isosceles triangle, we could go ahead and assume that these two sides are equal. And therefore, this is also 34 millimeters. So to find the perimeter, I'm just going to add up 34 plus 34 plus 32, which comes out to 100. And then I'll put the units of measurement, the millimeters. In fact, you have to put that unit of measurement. Failing to put the unit of measurement, you're going to get marked down. Okay, so make sure you include that. Okay, so that one wasn't very exciting. Let's look at another example. Let's say this time we're given a trapezoid. And how about it looks something like this. All right, we're told that this is 30 millimeters. This is 40 millimeters. And that this is 25 millimeters. There we go. Okay. So for this one, to find the perimeter, we do need the other side, but we definitely don't have that information. And because this isn't like some sort of isosceles trapezoid, I definitely am going to need to find this extra side here, this slanted side at the top. So to do that, so what we'll do is we're going to use the Pythagorean theorem. So I'm going to create a little right triangle up here. And this is going to be the same as the bottom of this trapezoid. That's going to be 30 millimeters. And here I can figure this little side out by subtracting the 40 minus 25. And that's going to come out to 15 millimeters right there, that little side. So I have the two legs of the right triangle. So I'll go ahead and call this the hypotenuse, which we usually label C. And according to the Pythagorean theorem, a squared plus b squared equals c squared. So 30 squared plus 15 squared equals c squared. So 30 squared, that comes out to 900. And 15 squared, that's 225. So added together, that's 1125. So then to find the hypotenuse, you might remember we need to take the square root of both sides. So the square root of that comes out to, well, I'm going to get a decimal. So here I'm going to write 33.5 millimeters. Now, that's not the answer. Actually, I shouldn't even put a box around that because that's just the missing side. So now that we have that missing side, we can now find the perimeter. So 25 plus 40 plus 30 plus 33.5. That's going to be, I came out with 128.5 millimeters again. All right. So we get the idea. Sometimes the information's missing and we have to kind of find it. Sometimes we're given like kind of creative figures where we are able to figure out the information. But yeah, finding the perimeter, honestly, that's as exciting as it can get. It's given some sort of missing information that we have to find out. Okay, so moving on to area, and area is far more exciting and has far more information. Before we kind of get into area, what we want to talk about is the concept of area. So area is the idea of how much space is being taken up, right? In fact, let me define area. Let's see if the book has a definition. They say the number of units it takes to cover a surface. Of units it takes to cover a surface. I actually really like this definition because it really depends on what unit you're using. For us, we typically talk about it in terms of squares, how many squares we use to cover an area. So we use what's called a small or a square unit of measurement. And what's nice is that if you want to kind of think of the idea that we're forming squares, it makes it a little bit fun if maybe something isn't a perfect square. So let's say, for instance, we have, let's do a 4x4 unit square, a little bit easier to draw by having it. Let's fix that. There we go. Okay. And let's say we pretend those are straight. We all have these kind of basic figures. I don't know what you want to call this, but let's say we have all of this shaded in. This kind of shape here. Pretend that's perfectly shaded in. Okay, not just scribbled on. All right, so if I wanted to find how much area is in this green region, each little square represents a unit of measure. And so clearly, the two that are already filled here in the center, right? These two right here, that would count for 2 square units. And then the other squares are half covered. So each of them would be a half a unit. So we would have 2 square units plus an additional 4 half units or half square units, which really ends up being 2 square units as well. Because if we put those 2 triangles together, they form a square. So that works out to being 2 square units. And 2 square units plus 2 square units is 4 square units. And that's the area that this particular green shape covers. And it's kind of fun to kind of do these shapes where you figure out how much is being covered by half units versus whole units and combining those together. So for us, we typically have 2 different ways we measure the standard units of area for America, the English units, and then of course the metric units. So we typically use square units in our basic measurement, which would be like a square inch or a square mile or square foot, right? Those are the typical units that we use here in America. So like, let's say for instance, we're looking at a square foot. Let's say I want to know how many square inches are in 1 square foot. So a square foot, we're talking about it measuring 1 foot on each side. And if we're interested in breaking it up then into inches, I would actually have to divide this up into 12 equal parts. So these will be 3, 3, half that, and then 3 again, 3 again. All right. And then doing that the other way. Oops, that did not go in the middle. Okay, 3, 3. Oops, let me fix that. All right, to the best of my ability. So how many of these little squares are there if it's 12 inches on each part? Well, that would be 144 square inches, which, by the way, we can abbreviate with the inches and the little power of 2. But really what we're looking at is this kind of conversion here. Because we're looking at 1 foot squared, we can think of that as 1 foot squared, kind of putting the squared on the outside. And since 1 foot happens to be 12 inches, we're really thinking of it as 12 inches squared. Well, when you square 12, that's 144. So when we talk about the conversion into square units, we literally have to square the number. Let's do this without a picture this time. Let's say I want to know how many feet are in a square yard. Okay, so I happen to know that 1 square yard equals, or I should say 1 yard equals 3 feet. So if I want to square that, I'm going to literally square it. So 1 squared is just 1, and 3 squared is 9. But now we're talking in units squared. So it would be 9 square feet, or feet squared, however you want to write that. And that's the idea behind converting in area. You actually literally have to square it when you're talking about squared units of measurement. Okay, so let's start doing some specific shapes. Let's begin with one of the most basic, rectangles, which is actually going to work for squares too, right? Because squares are a special example of rectangles. So the area for a rectangle is the length of the rectangle times the width. Or L times W. Or if you're really feeling lazy, a lot of people just write LW and don't even put the times symbol between them. Okay. So the length of a rectangle times the width of the rectangle. And that works for a square. It just happens to be that in a square, the length and the width are equal. Here, I should put a little right angle in the box so that way we know we're talking about a rectangle. Okay, so what's nice is it kind of extends to the same as a parallelogram. A parallelogram basically looks like a squished rectangle, right? Like a box that got sat on. So it has, rather than a length and a width, we give it a little bit of different label just so that we're distinguishing the two. Okay. So they call this the base. And then the slant isn't really given a name. Okay. But pretend I wanted to find the area of this. All right. If I knew some information, maybe kind of using our trick from before, I can make a right triangle here, which I also could make right here. In fact, this right triangle is the exact same as this right triangle. And if I were to take this right triangle and move it over here, that would look like a rectangle. And therefore, to find its area, I would need to do the base of the rectangle, which we would have that information. This would be the same thing as the base of the rectangle, but I would need this, and that would be the height of this triangle. So that's actually how we find the area of a parallelogram. It's base times height. But let's draw the base and the height a little bit cleaner, no longer moving things around. So this is the base, and the height would be that right there. Short way of writing that would be B times H, or of course, just BH. So we'd have to be given this information in order to be able to find this, or be given enough information for us to determine the area of this. All right. So let's look at an example. Let's say, I have another grid here. I'm going to do it in black this time. And let's say in this grid, each square is 1 centimeter. Here, I'll make it easy. Cut that off and try to make it look relatively even. Okay, so each one's 1 centimeter. All right, and let's say I have this parallelogram. Pretend, of course, that those are perfectly even and cutting very nicely and symmetrical. All right, so here's my parallelogram. I wonder if I can do a highlighter in blue. I can. Okay, here. The highlighter makes it color in a little bit nicer than I can do it with the pen. Apparently, though, it makes me look like I'm a child who cannot color nicely within the lines, but oh well. A little bit better in terms of the shade region. Oh, that was worse. Don't do that. I like that it actually tries to mimic what happens with a highlighter, right? Like every time you go over, it gets darker. All right, fine. I'll try to go over again just to make it look a little bit more consistent. All right, I'm done. There we go. So there's my parallelogram. Okay, so if each square is 1 centimeter, and I'd like to find the area, let me write that down, find the area. I could probably do that by just counting the base and the height, which isn't too complicated here. So the base in this case would be 4 centimeters. And the height would be, well, here, let me draw it on here. That would be, oops, a little too long. That would be the height, right? Right from here to here. And that would be 2 centimeters. Here, I should label that H. And then this is the base. Or here, let me just call it B. All right. So there we go. Base times height would be the area, which is 4 times 2, or 8 square centimeters. Square centimeters. I could probably find the perimeter of this too, using that information. Let's do that. Let's find the perimeter. So I happen to know what the base is. What I need though is that slanted length. And I might be able to use the Pythagorean theorem to help me. So here, I'm going to draw a little triangle based on my height over there, which I happen to know is 2 centimeters. And the base would be 1 centimeter. So I could find this hypotenuse here. So 2 centimeters plus 1 centimeter equals c squared. So that's 5. Just went ahead and jumped right into it. So the square root of 5. Let me grab my calculator and plug that in. I'm getting 2.2. You could even go 2.24 if you wanted. Why not? Okay, so then for the perimeter, it's going to be the 2 bases, which is 4 centimeters each, plus the 2 slants of 2.24. So that's going to come out to 12.48 centimeters, no squared. By the way, by putting the square on the units, anybody who looks at this knows we're talking about area. So having that squared units gives an indicator that we are referring to an area in that measurement. So that's kind of nice, a nice little clue about what we're working with. All right, so let's try one other exciting shape, and then we'll save the rest for the next class. And that is the triangle. Now the triangle, I'll just draw a scalene triangle here. A triangle can be kind of thought of as a half of a parallelogram, right? You can kind of imagine there being, a parallelogram here, right? So a triangle, the area of a triangle is literally half the area of the parallelogram, which is base times height. Where this is the base, and we still use the height measurement inside here. So that's the height. So 1/2 times b times h, or just drop all the multiplications and just write 1/2 bh. All right, so there we go. The area of a triangle is basically half the area of a parallelogram. Okay. And what's interesting is sometimes the height may not be as traditional. Let me give you an example of what I mean by that. So let's look at this one. Let's say we have a triangle with a base of 5.8 centimeters and a height of 2 centimeters. Clearly not drawn to scale. All right, so this triangle's area here, and I'm just going to do A for area instead of writing out the word, is 1/2 times 2 times 5.8. Well, actually 1/2 times 2 works out really nicely. That's just 1. So this comes out to 5.8. And we want to write centimeters squared. Do not forget the units. So here, we'll call that part A. So part B would be maybe an example of an obtuse triangle. So that'd be an obtuse triangle. Let's say this is 4 centimeters here. This time though, the height would actually be outside. So that would be 2.9 centimeters. But the area would still be found the same way. It'll be 1/2 times 2.9 times 4. Okay, so I'm going to use my trick where I'm going to pair up the 4 and the 2 because those are a little bit nicer to pair up, right? So 4 times 2, I'm sorry, 4 times 1/2 comes out to 2. And then 2 times 2.9, I will plug that in my calculator, 5.8. Exact same measurement. And I think that was intentional, by the way, for this particular problem. They had the same area, but different measurements. All right. Okay, so we'll stop there and then we'll pick up and finish the areas and looking at different shapes in the next class.